Alright, here we have a problem that's very similar to one we did before, except we did it sliding down a hill. This time we have a object rolling down the hill. In this case, it's a ring rolling down a hill from a height of h to the ground, has a radius of r. The hill has an angle of theta, and we want to figure out how fast is this thing going when it gets to the bottom of the hill. So you could solve this using torque and forces and accelerations, but it's much easier to solve it using energy considerations. So we're going to start there. So I'm going to, again, just first start by writing a conservation of energy equation, except for in this case, because the object is rolling and translating sideways, it has a velocity and it has an angular velocity. We're going to have to account for both of those types of kinetic energy in our equation. So we're going to start by saying, since this thing starts from rest, it has just gravitational potential in the beginning. We'll call A the top of the hill and B the bottom of the hill. At the bottom of the hill, it has kinetic energy due to translation, and it has kinetic energy due to rotation. And if we call the bottom of the hill's height 0, it has no potential energy at the bottom of the hill. Now we can, just like any other energy problem, we can expand these. So our potential energy at the top of the hill is just mg capital H. At the bottom of the hill, the translational kinetic energy is just 1/2 mv squared. And the rotational kinetic energy, this is something new that we learned about, is equal to, it's very similar to the translational kinetic energy equation, except for we use our rotational mass, which we call moment of inertia, and our rotational velocity. So this is going to be 1/2 moment of inertia times omega squared. Now at this point, if we want to figure out how fast it's going, we have two unknowns. We don't know the velocity of the part of our object, and we don't know the angular velocity of our object. But we do know, as long as it's not slipping, and it does say in the problem without slipping, that there is a relation between the angular velocity and the translational velocity, which is the angular velocity is equal to the translational velocity divided by the radius of the thing that's rotating. So we can substitute this in to our equation for omega, and this turns into, and I'm also going to substitute, it's a ring, so we know that the moment of inertia of a ring is also just mr squared. So we'll substitute that in for moment of inertia. We'll substitute omega equals v over rn for the angular velocity, and let's see what we get. So we keep mgh on the left, 1/2 mv squared for the translational kinetic energy. Now we have 1/2 for I, we put in mr squared, and for omega, we put in v over r, and that whole thing gets squared. If you notice, what happened is we reduced our equation to only having one unknown variable, which is the velocity of our particle, which is what we're looking for, which means we can solve this. Now it's just going about doing a little bit of algebra to clean things up. You might notice that we have an r squared here, and we have an r squared here on the bottom, so they're going to go away. We have, let's see, we're looking for the velocity, so we actually have an m in every single thing. We can drop those out. And this turns into gh equals 1/2 v squared plus 1/2 v squared, or equals just v squared. And we get that the velocity at the bottom of the hill is just the square root of g times h. And you might remember when we did the similar problem where if you drop something or if it slides down the hill without rolling, the velocity is the square root of 2gh. In this case, because some of the energy is going into making it rotate as well, it's not going as fast when it gets to the bottom of the hill, and its velocity is just equal to gh. Now, the second part here asks us, what if the cylinder were instead, what if it were a cylinder instead with a moment of inertia of 1/2 mr squared? So we can use our whole setup. We don't have to resolve the entire problem. It's still starting from rest. It still has translational kinetic energy and rotational kinetic energy at the bottom. The only difference is our moment of inertia is a little different. So let's start from let's start from the spots where we were this spot right here and rewrite this. So we have mgh equals 1/2 mv squared plus 1/2. Now this time our moment of inertia is 1/2 mr squared times, again, v squared over r squared. And similar things happen. The mass is in every single term. The mass is going to drop out. The r squareds are going to drop out. And we end up with gh equals 1/2 v squared plus 1/2 times 1/2, or 1/4 v squared, which is equal to, let's see, that's 3/4 v squared. So that means v squared equals 4/3 gh, or v equals the square root of 4/3 gh. In this case, since the moment of inertia was less, it was a little bit easier to rotate. So less energy was needed to put into making it rotate down the hill. And the velocity there ended up being a little more energy left over for the velocity. So the velocity was a little bit bigger, the square root of 4/3 gh, as opposed to the square root of just gh in the case where it was a ring.